The title of my presentation is the early excess power using NRL palladium boron cathodes. These are special cathodes that in my experiments, they've given excess heat almost every time, but they also show very early excess power. And that's the focus of this talk today, is the early excess power that shows up when you use these palladium boron cathodes. This is my presentation outline. I'm going to show experimental evidence, the results for 3 different experiments, one at Japan, NHE, another at Ridgecrest, California, the third at the Naval Research Laboratory. I had to go back. I didn't realize that showed excess power until I went back, looked at it in 2018. And then the second part of my presentation is discuss possible calorimetric error sources, because I thought this early excess power might be an error. I wanted to make sure it was correct. So the main error sources I could think of was the thermoneutral potential changing during deuterium loading, the cell heat capacity maybe being not quite correct, and the rate of cell temperature change. These are all very important parameters in the early excess power in the first term. I found that none of these really are an error source. So the excess power is real, and I think that's quite important. And then the third part is discuss possible boron effects for the cold fusion. What causes this early excess power? Is there a direct boron deuterium reaction? Is somehow boron an essential element for excess power? Maybe it makes the required nuclear reaction zones or vacancies, cracks, grain boundaries, and so on. Or it might even be a trigger that just gets the cold fusion reaction started, and then some other process might take over. The first experiment that showed this, the first one that brought this to my attention, was Martin Fleischmann, when he analyzed my data from Japan. He found there's excess power in the first few minutes. The first part of the experiment, there's excess power, and he made a comment that is obviously very important to establish whether this early excess power is, or positive, he called it positive feedback, is a property of the palladium boron alloy itself. And what I found out since is that it is a property of the palladium boron alloy. The second experiment I did was in China Lake quite a few years later in 2016. And the excess power actually showed up in the first few minutes, and it was up to 118 milliwatts at 8 minutes. And when I went back and looked at earlier results in the Naval Research Laboratory, experiments I helped set up, there's signs of early excess power there as well, and that used a Seebeck calorimetry. So 3 different laboratories, 3 different calorimetries, and they all show this early excess power. This is Martin Fleischmann's analysis, and he tried to show a lot of different things, and it's not too clear here, but you can go to page 81 of the NRL report, which is, you can click on my abstract to get to this report. But let me just trace the excess power. Each point is the average of 55 minutes. And you see it starts off here at about 55, 58 milliwatts, and it continues. There's still excess power. This line is what Martin thought was what you might get with loading, but it should be a little bit lower than that. And it continued for quite a few hours, up to about 27, 30 hours. And then it does drop back to 0. This is 0 right in here, and then it picks up again. But the other thing Martin shows here is the what is called the lower bound heat transfer coefficient. When the excess power goes down, it goes up and it reaches about its true value right here when the excess power is 0. This is Martin Fleischmann's analysis of the complete experiment over about 65 days. In the first day, these is the average of each day. And you see, even on the first day, it is a positive excess power. And note there's a certain period of time over a number of days where there's high excess power, and again later on, there's high excess power. That's Martin's analysis. Now, I did my own analysis before I left Japan, and I didn't know what the cell constant was. I finally figured it must be about 0.81, but that was really too low, and I didn't know what the heat capacity really was. NHE told me it was 490 because they'd used these cells before. But anyway, I show early excess power the first day, just like Martin did. I see this period of high excess power, and again, another period of high excess power. We have some negative values here because the cell constant was too small. The next slide is the Ridgecrest experiment. This was done in 2017, and I used a heat conduction calorimeter, my copper calorimeter. And this is the first minute, second, third, up to 8 minutes. At 8 minutes, the excess power is 118 milliwatts at 8 minutes. It fell back down, it came back up. And if I take the 55-minute average to compare with Martin, I'm in about the same ballpark, the same amount on the average as what he reported. And it does gradually go down, as Martin found also, but then later, the next day or two, it does pick up again. This is the experiment in January 1995. I helped set this up at Naval Research Laboratory. They had a new seabed calorimetry, and Roger Hart, the one that owned the company that made these, he spent a week before this experiment making sure everything was working and it was properly calibrated. And this is the beginning of the experiment. Now, some of this is due to loading, but the loading should have fallen back down to about 0 at 20 minutes, 20 hours, I mean, and it continues. The excess power doesn't allow you to see that because it continues on, and it continues on for quite a few hours. And it even goes on and gets up, not really high, but up to about 15 milliwatts. And later on, they had a problem with the calorimetry because they had the gas lines, instead of going straight up, they went horizontal, and they became clogged with the D2O vapor that condensed to form D2O liquid, and then the data was useless after that. The possible calorimetric error sources that I spent the last couple of years looking for, I focused first on the thermoneutral potential based on just the loading, the reaction, all the deuterium going into loading. I thought this might be the cause of the early excess power. And it does make the thermoneutral potential lower, but not low enough to explain the excess power. In fact, it provided me a new way to calculate what is the maximum excess power due to loading if all the deuterium goes into the palladium. You can calculate it by this simple equation. It's a lot easier than what I was doing before. And this maximum it could be was about 27 milliwatts. That's not enough to explain the excess power that I observed. Going to another possible error source is the cell heat capacity. From Martin's studies of my data, he came up with a value of 450 joules per degree. And I checked that by doing the calculation, 90 milliliters of D2O, 419. The inner glass that changed temperature, it was another 30. Platinum metals, they don't add much, but 2 joules per degree, and I calculate 451. So I don't think there's any error with this. And besides, if you have the wrong heat capacity in Martin's calorimetry, you go across the heating poles, the temperature changes rapidly. And if you don't have the heat capacity correct, you have a discontinuity there. And if you can read this in the NRL report on page 72 and 73 for more details. The third possible error source is the rate of temperature change with time correct? But I think you can accurately determine this rate of temperature change with time. You can graph the temperature versus time and get the slope at any point. You can fit a polynomial to the temperature. That'll give you the equation to calculate the change of temperature with time at any given point in time. And I haven't done that much with this, but what little I've done is quite accurate. And and you could avoid the DT, the change of temperature with time completely just by integration. And I've done this as well. You can use the Simpson rule, trapezoidal rule. These are recommended by Fleischmann. In the integration, you change rate of change of temperature and watts as an answer to cell heat capacity times the actual temperature differences between two different times, and it'd be in joules. And this gives good agreement with what we measured by using the rate of temperature change with time. Going on to the next one, and I don't have much time for this, so I'll kind of skip over it, but Fleischmann always said the first thing you should do in a calorimetric study is assume the excess power is zero and calculate what he calls the lower bound cell constant that results if you assume the excess power is zero. And then you can find the real excess power later when you know the cell constant by their difference times the difference in temperature at any point. And this works very well. This is accurate. It's not an approximation. But if you rearrange this equation, you can see that very early in the experiment, if you have excess power, you're dividing by a very small delta t. And so this negative term dominates, and your lower bound cell constant will often be negative if you have real excess power. And this is what I found in these experiments. It stayed negative for about 12 or 14 minutes before it went positive. And then this just shows an example of how you, from the data, how you can use this equation up here to calculate the excess power. And it agrees very, very well with other methods. But for details, go back to Martin Fleischmann-Pons Physics Letters A paper, and you can read all about this lower bound heat transfer coefficient. So what are the effects of boron? Right? With excess power early on is real. So what can explain this? Boron may be an essential element somehow for LENR. Uh, it may explain why if you don't add boron on purpose to the cathode, it may take weeks and months of electrolysis before you transfer boron from Pyrex glass. That's what most people use. Pyrex glass contains boron, and it leaches out and gets deposited at the cathode. And we explain why that you have that long delay. And it explains also, in my experience, if you run the same cathode a second time, a third time, a fourth time, often the excess power gets larger. That could be because you now have the boron already present that was needed. Boron may participate in the fusion reaction. A D plus B boron 10 gives you 3 helium 4 and this amount of energy, 17.6 MeV. Tom Passel has studied this and reported this in ICCF-6 and ICCF-C11. And he's found actual boron 10 depletion in active electrodes, but not enough to really prove this, but it does indicate that this might be, boron might be a participant in the reaction. And boron may aid the creation of these special reaction zones, vacancy cracks, and so on. It may act as a trigger. It might be just needed to get the reaction going. Maybe another reaction takes over later. And I put this in because another big difference with boron, it loads normally, but the deuterium comes out much slower. They're deloading. It takes days and days to get all the deuterium back out because boron, I think, sits in the grain boundaries, and the boron tries to get out. I mean, the deuterium tries to escape by the grain boundaries, and it can't do that very fast. And boron, we know in chemistry, is an unusual element, has 3 unpaired electrons, and unpaired electrons, according to the NMR spectra people, it can affect the NMR spectrum. So it's affecting the neutron somehow, affecting the nucleus, I mean, somehow. Dynamic nuclear polarization, if you want to read more about that. And calcium boron often used in the palladium preparation. So there might be some boron always present, a small amount, especially in the Johnson-Matthey. The Johnson-Matthey palladium used this calcium boron. And again, going into mathematics, you can write the differential equation and you assume the excess power is 0 and see what you get. how fast should the cell temperature increase if there's no excess power? You can simplify this equation by defining alpha and gamma, and then becomes this. Can't go through the mathematics, but it's a nice little mathematical exercise. Martin, because of Martin pointing this out to me, he derived this first, and this is the change of cell temperature with time. It's an exponential relationship, and it seems very accurate. If the time is very small, this exponent is small. And we know the small exponent, e to the minus x, is approximately equal to 1 minus x. And then very early times, like say the first 5 minutes, the temperature should increase linearly with time. And I see this in nearly every experiment. Starting off the experiment, the temperature is increasing the same amount each minute or each 2 minutes. Quickly, my experiment in Ridgecrest, this is what I calculate if there's no excess power. This is what I measured experimentally. You see in every case, like 10 minutes, the experimental temperature is higher than what I calculate. And if you take that difference between 0.675 degrees and 0.540 degrees and multiply that by the heat capacity of the cell, you get 61 joules. And if you average that over 10 minutes, you get joules per second, which is watts. You get 0.102 watts or 102 milliwatts. Well, if I take my measured data over those first 10 minutes, these are the measured data, and I take an average of that, I also get 102 watts. So it shows these two different methods give about the same result. But it's kind of fortunate it came out that way, because the standard deviation is plus or minus 13. So I was a little surprised it came out exactly the same. But I think it helps to show that excess power measurements are correct, that are measured by my Ridgecrest calorimetry or other calorimetry. The summary, the early excess power has been measured in 3 different experiments using 3 different calorimeters. And they all show this early excess power. I can find no error source that explains this early excess power. And I've looked very hard for the past 2 years at the thermoneutral potential, the heat capacity of the cell, and the rate of the cell temperature change, because these could be the error source, but I don't find any evidence that they are. The possible boron effects for cold fusion, it could be entering a direct reaction with deuterium. It might be an essential element somehow. It may aid in creating the nuclear reaction zones, or the nuclear active environment, as Ed Storms like to call it. It may serve as a trigger for getting the fusion reaction started. There might be some other reaction that takes over later. And they're very different in loading and deloading, with boron present than pure palladium. And finding the acknowledgements, Mr. Sumi helped me set up these experiments in Japan, and I wasn't allowed to take the computer data with me when I left. I was disappointed in that, but maybe not, perhaps without permission. After he left NHE, he sent all the data to me by computer. It was a very long email, and I provided this data to Martin Fleischmann. He did the analysis, and he's the first to point out this early excess power. I never previously thought to even look at that first early period, because I thought you couldn't measure anything accurately during that period. But Martin found otherwise, and I've now since found otherwise. Dr. Imam, for making these materials at Naval Research Laboratory, and even has a US patent on this. If you want to read details on how it's made, the patent is right here. Dr. Fred Sawfield, he's head of NRL in 2001, when we tried to get this NRL report published at NRL. A lot of people didn't want it published by NRL, but he was the head of NRL, and he ruled that it could be published. And so it got published as an NRL report, not without controversy, however. And I thank Martin Fleischmann and Stan Pons for their accurate calorimetric equations. Every time I've checked them, they're correct. They turn out correct. And then financial support over a number of years from an anonymous fund at the Denver Foundation through the Dixie Foundation at Dixie State University. Okay, thank you for your time. And if you have any questions, email them to me and I'll be glad to answer. Thank you.